Hey guys, welcome to the video tutorial. It's really going to be about circular motion and whatnot, but it's really designed to help you with physics. It says Orbits Worksheet 2. And so what we're going to do is we are going to start with number 6. And number 6 talks about, it says, a satellite with a mass of 20 kilograms is in an elliptical orbit. So here I've got an elliptical orbit, and I'm going to put the Earth, let's say, right here. And so the Earth is at one of my foci, and then I've got my satellite somewhere out here. And so the mass of the satellite, it says, is 20 kilograms. And then I'm going to just go ahead and give you the mass of the Earth is, again, 5.97 times 10 to the 24th kilograms. And let's read on. It says, elliptical orbit around the Earth at the perigee, the point nearest the Earth. So I just so happen to have a orbit going on right here. And so let's say that, and this is a sun, but let's just pretend it's the Earth and whatnot. And so the perigee is right there, right where it's closest to this object, okay? And so if we start that again, right there, oh, I pushed the start button, right there. It's pretty hard to stop it because it moves so fast, but right here would be the perigee. That's the closest it gets to the Earth. And it says that that distance is 8.0, and it says times 103, but it's times 10 to the third. So this distance right here, the perigee, is, what did I say it was? 8.0 times 10 to the third. So perigee is 8.0 times 10 to the third meters. Now, the other distance, the apogee, is 1.6 times 10 to the fourth. So the apogee, which is the furthest distance, is 1.6 times 10 to the fourth meters. So that is the apogee. And so what they ask for, or what I asked for rather, is it says, okay, and so the other thing I tell you is that it's traveling at 8.26 times 10 to the third meters per second at the perigee. So the velocity over here is 8.26 times 10 to the third meters per second. Okay, and then I say at the apogee, we have a velocity of 4.29 times 10 to the third. Okay, which is what we'd expect. I mean, if you just look at this simulation here, we're moving slower at the apogee, and then we get faster and faster and faster until we hit the perigee, and woo, we're at our top speed. So, the speed at the perigee is obviously greater than the speed at the apogee. So, part A deals with the perigee, and they want us to calculate the potential energy. So that would be U gravitational. They want us to calculate the kinetic energy. Ooh. So we're going to get back into our kinetic energy equation. And then they want to know the total energy. Well, all that is the gravitational potential plus my kinetic. So U gravitational plus kinetic energy. Okay. So the equation for potential energy due to gravity that we talked about today was negative G M1 M2 over R. M1 and M2 being the two masses that you're talking about, and R is the distance between their centers. So here we've got two distances that we're going to use respectively for A and B. Kinetic energy, if we remember, is 1/2 mv squared. M being the mass of the object that's rotating. In other words, this would be the mass of my satellite, and v would be the velocity of the satellite. So let's work with the gravitational potential energy first. So U grav equals. So I've got negative, and then on top I've got g, which is 6.67 times 10 to the minus 11 times m1, which I'm going to make m1 the mass of my satellite. So it is 20 kilograms. Times the mass of the Earth, which is 5.97 times 10 to the 24th. All of that over, and again, we're talking about the perigee, so all of that over the distance at the perigee, so that is 8.0 times 10 to the third. So, doing this in my calculadora, I'm going to do the top first, and then I'm going to divide. So, the top, 6.67 times 10 to the minus 11th times 20 times 5.97 times 10 to the 24th. So on top, you should get 7.96 times 10 to the 15th. And then all of that over 8.0 times 10 to the third. The last step is just to divide those. So I'm going to go divided by 8 times 10 to the third. And your final answer should be 9.95 times 10 to the 11th. So, net and the negative. So U gravitational should be negative 9.95 times 10 to the 11th power. And that is in joules. Okay, so we've got the gravitational potential energy. Now let's figure out the kinetic energy. Well, that's pretty straightforward. Kinetic energy is just 1/2 times the mass of my satellite, which is 20. So far, pretty good. Times my velocity, which is 8.26 times 10 to the third. So really, you can do this all in one step on your calculator. Half of 20 is 10. 10 times 8.26 times 10 to the third should give us an answer of 8.26 times 10 to the 1, 2, 3, 4th. Hey, that's weird how that worked out. We multiply by 10 and we get an extra number up here. That's how that works. So 8.26 times 10 to the 4th joules. Okay. So that is my kinetic energy. That is my gravitational potential energy. So my total energy is just added those up. So E total is just 8.26 times 10 to the 4th plus negative, so I'm just going to go ahead and go minus 9.95 times 10 to the 11th. So that gives me a total energy of, so minus 9.95 times 10 to the 11th. That gives me a total energy of negative 9.95. Hang on just a second. 8.26 times 10 to the 4th, and then minus 9.95 times 10 to the 11th. Okay, so that gives me an answer of negative 9 point, and it's like 949999999. So really, my kinetic energy isn't making that much of a difference compared to my total energy. So it's 9, we'll go 9499 joules, or times 10 to the 11th joules. Okay, so that is for the total energy at the perigee. So now part B asks us to calculate these same values but at the apogee. So B, my gravitational potential energy, it's the same equation, but now R is going to be the distance at the apogee, which we said was right here, 1.6 times 10 to the 4th. So you do this same equation. negative 6.67 times 10 to the 11th, negative 11th, and then times 20, the mass of my satellite, times 5.97 times 10 to the 24th, all over, but now my radius is, what do we say it was? 1.6 times 10 to the 4th. So 1.6 times 10 to the 4th. So that gives me, again, I know what I'm going to get on top because I've already done that. I should get 7.96 times 10 to the 15th. So now I'm going to go negative 7.96 times 10 to the, was it the 14th or 15th? It was the 15th. Times 10 to the 15th. And I'm going to divide that by 1.6 times 10 to the 4th. Okay. So we go 7.96 e to the 15th, and we divide that by 1.6 times 10 to the 4th, and that gives us 4.975 times 10 to the 11th. So our gravitational potential energy, or U-grav, is negative 4.975 times 10 to the 11th. Okay, so then kinetic energy is again 1/2 m, which is 20, times my speed at the apogee, which was 4.29 times 10 to the 3rd. So 4.29 times 10 to the 3rd. So plug that in your calculator. 10 times 4.9 times 10 to the 3rd gives me 4.29 times 10 to the 4th. And again, both of those are in joules. So now we're going to calculate our total energy. And so we're going to add those up. So 4.29 times 10 to the 4th minus 4.975 times 10 to the 11th gives us an answer of negative 4.975 times 10 to the 11th. So again, not much change due to our, because most of our energy is coming from our gravitational potential energy. So, and again, I'm going to double check this just to make sure that that is correct. So, real quick, bear with me for just a second. 6.67 e minus 11 times 20 times 5.97 times 10 to the 24th, 15th, and then divide that by 8. Okay, good. Okay, so that is how you do the first problem there. So now we're going to move on to problem 7. And problem 7 talks about, it says a 1.0 times 10 to the 3rd kilogram satellite orbiting at 3.0 times 10 to the 8th meters from the Earth's center. So here is the Earth, and then here is my satellite, and it says the mass of the satellite is 1 times 10 to the 3rd kilograms. And then the mass of the Earth is again 5.97 times 10 to the 24th. And it says the orbiting distance is 3.0 times 10 to the 8th from the Earth's center. So our distance, or our R, is 3.0 times 10 to the 8th meters. Okay. And it says it encounters a mishap and falls to the Earth. So calculate the speed. So all they want to know there for A is orbit, which we know is just the square root of g times m over r. m being the mass of the central object. So in here, the central object is the Earth. So you're calculating orbit in A. B is the kinetic energy, so you're just using that speed that you get, and you're using that for kinetic energy. And then C is the potential energy and the total energy before it starts to fall, blah, blah, blah. So let's calculate the orbit. That equals the square root of, so we've got 6.67 times 10 to the minus 11th times the mass of the central object, which is the mass of the Earth, which is 5.97 times 10 to the 24th. And then all of that over the radius, which is 3.0 times 10 to the 8th. And then the square root of that whole thing. So I am going to do this fraction first, then I'm going to multiply, then I'm going to square root. So again, I've got the square root of 6.67 times 10 to the minus 11th. And then times. So let's simplify our fraction. We've got 5.97 times 10 to the 24th. Divide that by 3 second e to the 8th. So that gives us a fraction, or an answer of 1.99 times 10 to the 16th. So multiply that by 6.67 times 10 to the minus 11th. So we're getting, that equals the square root of, let's see, that would be 1, 2, 3, 4, 5, 6. So 1.33 times 10 to the 6th. 1.33 times 10 to the 6th. So square rooting that gives me an answer of 1,152 meters per second. So my velocity is 1,152 meters per second. Okay, so now for part B, I'm going to write B over here. B, they want us to find the kinetic energy. So again, that's 1/2. Now m here is the mass of my satellite times the velocity of my satellite. And that's 1/2 mv. Ooh, you know what we didn't do up here? I don't think I squared velocity. I sure didn't. Whoopsie pie. So, go back through on your kinetic energy equations and get, this should be v squared. So 1/2 10 times 8.26 times 10 to the third squared. I'll just do the kinetic energy times here real quick. This is A on number 7. So 10 times 8.26 e to the 3, and then that answer squared. Ooh boy, that's a little bit different. Okay, so that is 1, 2, 3, 4, 5, 6, 7, 8. So 6.823. 6.823 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. Whoops! Joules. So that will change our total kinetic energy. So again, just swap that out and add it here and do the same thing for part B. Okay. Now, moving back to, again, you can pause the video here, go back and fix those answers, and then come back to this part. So 1/2 mv squared, silly. So here the mass of my satellite is 1.0 times 10 to the third. So kinetic energy, Ke, equals 1/2. The mass of my satellite is 1.0 times 10 to the third. And then V, we just found, was 1,152, that squared. So, plugging that into my calculator, I've got 0.5, which is 1/2, times 1 e to the third, times 1,152 squared, gives me an answer of, oh boy, that is a lot of kinetic energy. That would be 6.64 times 10 taken to the 1, 2, 3, 4, 5, 6, 7, 8, times 10 to the 8th power. And again, that is in joules. Last thing is to calculate the potential energy. So you use your U-grav, and that is negative G M1 M2 over R. So here M1 and M2 are the mass of the satellite and the mass of the Earth, and then r is the distance at which it is orbiting. So, plugging all that into your calculator, and again, I'm just going to do it on here, but check yourself before you wreck yourself and make sure that you are doing it right. So, times 1 e to the third times 5.97 e to the 24th. And then divide that by r, which is 3e to the 8th. So you should get a potential energy of 1, 2, 3, 4, 5, 6, 7, 8, 9. 1.33, negative 1.33 times 10 to the 9th power joules. Part D is just the total energy, so you add both of those up, and that gives you your E total. So E total is just your U-grav plus your KE. Okay, that's number 7. Now, number 8, you're doing the same thing, but now you've got a 10 kilogram satellite, but the trick here is that your, and again, I'm going to erase this, so if you're not at a stopping point, you can just pause the video. Just an idea. Oh boy, that eraser sucks. Here's what I'm going to do. Your number 8, I'm running out of room, so I'm going to write it down here. Number 8 talks about a 10 kilogram satellite is in orbit, and it says it's 200 kilometers above the Earth's surface. Okay, so here's the Earth, but my satellite is 200 kilometers, not kilograms, 200 kilometers above the surface. Part A is the potential energy, so you're using U-grav, but R is going to be the radius of the Earth, okay, which you should have written down in your paper, plus 200 kilometers. So you need to convert 200 kilometers to meters. You're using that for R. Now the kinetic energy of R, you will need the velocity. So you're going to have to calculate Vorbit. And then the additional, don't worry about part C. Part C we're going to work on tomorrow. So, finish up number 8, and then utilize the rest of this video to finish up number 8, and then come ready to hand this worksheet in tomorrow.